Okay, so let's take a look at quantum computing. I used to use an IBM service that would let you use an actual real quantum computer, and it also included a Python emulator, and that seems to be gone or changed, so it's too hard to use. So then I wanted to just run the Python emulator of a quantum computer myself, and it turned out to rely on some strange libraries that were hard to find. So I couldn't do it in normal Python environments. And I found for some reason this thing called Python Anywhere is the one that is the environment that allows you to install the software you need. And it does have a free service. So uh, that's where I ended up. You make a free account, and then you have a dashboard. So let me put an image of this to the side here. If some of you are experts at Python, you might know how to set this up in other environments. I just hunted around until I found a free service that would let you do what we need, and didn't struggle beyond that. So I should be able to have a bash console here. I can have up to 2. Okay, I'm ready to delete the old ones if I can figure out how. Minus. Why don't I use an existing one? Well, I'm in something. Let's see if I can figure out how to delete these old ones. I may not be able to do it. 3, 2. Oh, there they go. Good. The minus sign is taking them away. Fine. There we are. Now I can hit the plus to make a new one. That's what I wanted. Okay. And here's how you install Project Q. First, you upgrade pip, the Python package manager. And then you install Project Q, which is the quantum emulator. All right, it's updating from pip 23 to pip 24. I don't know if that's strictly necessary, but anyway, should work. All right. Now I install Project Q. And there it goes. Apparently it was already on there. Maybe it remembers my environment from the past. Okay, so now I can create my first quantum simulator, Q1, and it looks like it remembers these from before, which is okay. So what's going on here is you import some libraries. Then I'm going to make a default qubit. Now, in normal digital computing, you have transistors that have states of 0 and 1, and you have logic things like flipping a bit from 0 to 1 and doing an and doing an or, an XOR. Those are the sort of things with the truth table. And those at that fundamental level, if you consider how one bit is transformed by the elemental operations, that's where quantum computers are different. This is going to create a qubit in state 0, and 10 times it's going to measure a qubit. And this is the beginning of understanding quantum mechanics. In quantum mechanics, qubits are often in uncertain states, where they have a probability of being 0 or a probability of being 1. And if you measure them many times, you'll get a probability of 0 or 1. That's why you get in the habit of measuring it. When you measure it, a qubit stops being uncertain and the wave function collapses down to a single state. So we're going to measure it 10 times. We're going to make a new qubit and measure it, then flush to clean out the old stuff, and then do it again and print them out. That's all this is going to do. So I save it and run it. Should be /Q1. Oh, Python. Okay. Python Q1. Okay. Okay, so it allocated a qubit in state 0, and it measured it 10 times. And this is not an uncertain state. This means essentially the same thing as a normal bit in state 0. So, of course, every time you measure it, you get 0. So that's an easy situation. Now, we're going to flip the qubit, and that's why I was just updating this image to get it run. It's easier to see. This is what's called the block sphere by the developer of quantum mechanics, block. So in normal computing, all you have is a state 0 and a state 1. But in quantum computing, you can be anywhere on this sphere. So if you start in the state 0 and you rotate by 90 degrees about, say, the x-axis, your qubit will rotate down here to point along the y-axis, and now it has a 50% chance of being a 0 and a 50% chance of being a 1. And if you rotated it more, it would be more likely to be 1 than 0, but still have some degree of uncertainty. And these uncertain states mean that a single qubit is in fact a three-dimensional analog object with two numbers to define it, this angle and this angle. So it contains much more than one bit of information. And this is what makes quantum computers so powerful. Each bit is not one bit. Each qubit is much more. Each qubit is really two floating point numbers. And you would need those floating point numbers to be at high precision to actually do something useful like crack a 1024-bit RSA key. And unfortunately, the current generation of hardware, these has a lot of noise in the bits. So these numbers are in fact low precision floating point numbers, and you can't really get much accomplished with the current generation of hardware. But if it gets a lot better, then we'll be able to perform operations these way with qubits and perform quantum operations. So what we're going to do, we're going to make the Q2 here, and this is going to import X. It's going to create a qubit in state 0 and measure it, and then a qubit in state 1 and rotate it around X and then measure it. And we'll see how that comes out. So this is going to be, I think I can just cat Q2. I think I've already got these in here. Okay, so this makes qubit in state 0 and measures it 10 times, just like we did before. This makes a qubit, and it allocates it, and it rotates it by X. And that should turn it into a state 1. So let's try this with Python Q2. All right, so we had a qubit in state 0, and they rotated it 180 degrees around X, which made it a qubit in a certain state of 1. So we still haven't gotten anything new here. We've recreated the situation of normal digital computing. In normal digital computing, these are the only two states you ever use, a certain of state 0 and a certain state 1. Now we're going to move up to uncertain states, which are the ones that do called superposition states, where you have a superposition of some 0 and some 1 combined. And that's represented by the red arrow, if there is one here. I haven't got it, I'll have to add it. But anyway, an arrow pointing in between, where you have it. All right. So you use a Hadamard gate, is the name of the transition that moves the qubit into a superposition state containing equal amounts of 0 and 1. So this one, instead of transforming it with the X operation, we transform it with the H operation, and then measure it 10 times. So this one is our original quantum qubit in state 0 that is not going to change. And this one starts in state 0 and runs it through a Hadamard transition, which makes it into an uncertain state. So we get now we get a superposition state that has a 50% chance of being 1 and a 50% chance of being 0. So every time you measure it, you'll get a random chance of those two bits. That's the uncertain state superposition of 2. And now in digital computing, you have simple ways of combining two bits like and or. But in quantum computing, you have this magic state called entanglement, which is not at all present in classical physics. And this is something that Einstein originally regarded as a proof that quantum mechanics was nonsense. You can have two particles that are entangled so that if one is positive, the other has to be negative along a parameter. And even if you separate them far apart and measure one, you already know what the measurement of the other one will be. And this implies that some kind of signal is sent over a large distance faster than light to tell the other particle that you measured its entangled particle. And he said, that's insane, that's crazy. And it turned out to be the way the world really works. He designed the Einstein-Podolsky-Rosen experiment as an experiment to prove that this was nonsense. And when they tried it, it actually worked. This is the way the world really works. So we're going to entangle these qubits, and you do that with the C0 operator. So first we take a qubit, we make two qubits, then we rotate one with Hadamard, so it's uncertain, and then we entangle the two here, and then measure them. Now, if they weren't entangled, the one we rotated would be in uncertain condition. It would be half one and half zero, and the other would be all zero. But now that they're entangled, they have to always be the same. So this is, I think, probably Q4. Yep. Okay, so let's take a look at Q4. All right, there it is. It runs the Hadamard gate to make it uncertain, make one of them uncertain. It entangles the two, and then it measures both of them. So if we run this through Python, now here's the two bits, and the point is one of them was uncertain, the other one was entangled, so they always have to be identical. So the one that is now in a superposition state is going to drag the other into a superposition state too, because they're entangled, even though it would otherwise have been in a certain state. And this is a physical property between qubits that you have to make in your hardware. And this also has to be an operation that happens to high precision. And this also is the current generation of hardware also has a noisy version of this entanglement. And in order to really do good quantum computation, you have to have qubits with low noise, and you have to have interactions between the qubits of low noise, which is why they talk about cooling them nearly to absolute zero and crazy expensive things like that to make them work. So that's the game. Now, we can make circuit diagrams of these things that look like, so here's Q5. Let's see if I have that. I think I've got them all here, which is nice. Yep. Okay, so we import some libraries, and there's a drawing engine now. And so we allocate the qubits. We do this one where we rotate one by Hadamard to make it in an uncertain state, and then we entangle them with quantum entanglement with C naught, and then we're going to print a drawing version of that. So the output of this is going to have to be put in a text file. It doesn't have the ability to display graphics directly in this terminal. We can save it in text, and then we can download that file. So I have to click Files. They're supposed to be somewhere on my screen here. Up here, maybe? Files, okay. Maybe I have to, oh, there it's coming, just slow. Okay, good. And in here, I should have a q5.txt, which is here. And this was created today. This is good. So I download it. Okay, right click the down arrow and save link as. All right. And put it somewhere like downloads. Okay, now I have q5.txt. Okay. Now, it can't display a text file instantly. I have to use like a site to turn it into a PDF. That's why these parts are kind of clumsy, but such is life. So here I can take my input file, which is going to be q5.txt, and my output format can be PDF, and I can convert. Okay, and where's the answer? Here, running. Okay, there it is. Download. Okay. q5.pdf. There, I finally got my circuit diagram, which is here. So I should be able to view that. And there it is. I just need to zoom in on it a bit. Okay, so that is the circuit diagram of the thing we have just made. Here's two qubits that come in. They start as zero. This one is rotated with the Hadamard gate, and then the two are entangled, which is what this symbol means. That's what happens. All right, that's how you can draw graphic versions of these quantum circuits. All right, so now we can make a circuit with 3 qubits with this one, and I think I'll just download it. I think I've already got it here. You run this and create it. Then I should be able to, that's going to be, well, I guess I'm going to make it because I'm not sure what the name would be. So let me go back to my console. Okay. I don't know why I have 2 of them. It doesn't really matter. Let's see. I think it might be Q up to Q6. Let's see what I have. I don't have Q6. All right, I'm going to just call this one Q6. So I think I'm not going to bother. All right, so you do this one. Here you're going to have 3 qubits. This is what we had before. One rotated to an uncertain state and one entangled with it, and another one just rotated to an uncertain state alone. And so if you run that, you'll see this pattern. The first 2 always match, and the third one is random, but uncorrelated with the first ones. That's the sort of thing. And there are a few more challenges down here where you get to build these circuits and see them go. And the reason you do all this is because you want to crack encryption. So let me bring up the Shor algorithm, which is the motivation for any of us caring about this, is Shor's algorithm. Shor's algorithm here. And here it is at Wikipedia. Short, and it will have a diagram out someplace. There it is. This is Shor's algorithm. And this has all these Hadamard gates and all these issues of entanglement, and you have a whole bunch of these things, and you can do something called the quantum Fourier transform. And the point is, this is an analog computing device that factors numbers into their prime components. It is analog, not digital, and it's hardware. You design different hardware connections between the bits to get the job done. It takes you back to really old form of computing before general purpose computers and microprocessors. And if you think about this, there already are devices like this. For example, a flute. You blow out of your mouth making white noise, and the flute is designed so certain frequencies cancel out and other frequencies are amplified. So you get a pure note. And this Shor algorithm piece of hardware is designed so that when you feed in an encoded number that is the product of 2 primes, it will send signals through this hardware which cause the factors of those primes to come out the other end. It does not do a calculation on a possible factor and then try the next one and try the next one after another in an algorithm. It doesn't have a loop. It doesn't have that kind of logic code. It's a piece of hardware that is designed so when you feed it an encoded number that's the product of 2 primes, the output will show you the underlying primes. And that's why it's really fast, and it doesn't matter how big the prime numbers are. You just make this whole array bigger. That's why I say even going to 1,000,000 bits would not save RSA. If this stuff worked, the whole logic of public key encryption would be shot based on RSA or any of the current systems. And that's why we have this other weird system about learning with errors, where when you encrypt something, you add errors to it to make the output random. And when you try to decrypt it, those errors make the decryption fail unless you have the secret key. That's the modern technique, the lattice encryption. So wanted you to see that. And it's, again, a little bit mind-bending, and this is the world we have to get used to. So I'll stop that one.